All right, Rolle's theorem says if f of x is continuous on some closed interval a comma b and differentiable on an open interval a comma b, and if the value of the function at the endpoints are equal, if f of a is equal to f of b, these are all conditions, if all of these three things happen, then Rolle's theorem says there must exist at least one value x equals c on this interval where the derivative at that value is equal to 0. That's what Rolle's theorem says. So we're going to consider the function from the previous page, aka the previous video, and we're going to see if Rolle's theorem applies on these two intervals here, 2 to 14 and 2 to 10. So if you look at the graph or the table from before, you will see that, well, f of x is continuous. On that closed interval, 2, 14, so that's good. It's differentiable on that same interval, so that's good. And f of 2 is equal to 5, and f of 14 is equal to 5. So yeah, since all three conditions are met, Rolle's theorem is applicable. We're just testing the conditions here to make sure that we understand how the theorem would work. So then let's check out the closed interval from 2 to 10. So we're going to test the function f of x. This is the same one that we just plotted before on the previous page. It's continuous. There's no discontinuities from 2 to 10. It's differentiable on 2, 10. And we know from before that f of 2 is equal to 5, and let's see, f of 10 is equal to 10. They are not equal, so because of that last condition, Rolle's theorem is not applicable over this interval, meaning that there's no guarantee that there's some value in between here that has a derivative equal to 0. So let's keep looking at this and actually apply the theorem. So for each of the functions below, we're going to determine if Rolle's theorem is applicable or not, and then we're going to apply it to find the value of c. So we've got this polynomial function on this closed interval. So g of x, it's a polynomial function, so it's definitely going to be continuous, is continuous on -3, 0. And it's definitely differentiable, so it's differentiable on the open interval, -3, 0. So now we've got to see what g of -3 is. It's going to be 9 times 9 minus 81, which is 0. And g of 0 is also equal to 0. So now we can see that Rolle's theorem is applicable, and we can use it. So we've got to actually find the derivative. g prime, and we're talking now at the specific value c. We're looking for c. So g prime at c is equal to 18c minus 4c cubed. And Rolle's theorem says that there's some value for c where the derivative is equal to 0. So we're looking for when it's equal to 0. 0 is equal to 18c minus 4c cubed. And we can go ahead and factor and solve. So we can factor out a 2c, and we're left with 9 minus 2c squared. And we can use difference of squares, 3 minus square root of 2c, and 3 plus square root of 2c. So here we'll find that c is equal to 0, and plus or minus radical of 3 over 2. And what we've got to do is look at the interval and the domain. C is an endpoint, so that doesn't work because Rolle's theorem says that there's a value way up here on the open interval. It doesn't include the endpoints. And if we think about that domain we were given here only from -3 to 0, this tells us that it's got to be the negative value here. That at the point c equals negative radical 3 over 2, you will have a derivative equal to 0 for this function g. If we were in class, I'd ask if you have any questions, but we're not, so I'm going to keep going on to number 2. Here's our function g of x. We need to see, is it continuous on this interval? That's the first condition. Well, here we've got an asymptote at x equals to -2. So g of x has a discontinuity at x equals -2. Therefore, Rolle's theorem is not applicable. I should be more specific here. Has a discontinuity at x equals -2, and -2 is within the interval that we were given. If -2 was outside that interval, that would have been okay.